3, 2, 1.
Here we go!
Alright guys, and welcome back. Now that we have our feet on the ground, let's talk about a target type that I don't do much imaging of that I'm going for tonight and possibly tomorrow, and it's called Dark Nebulae. Okay, so you guys are about to get a lot of information. If you don't want all of the information about how stars form and how this dust all starts collapsing in on itself, skip to the next chapter because this might not be for you. So what exactly are dark nebulae? Dark nebulae are interstellar clouds that contain a very high concentration of dust. This allows them to scatter and absorb incidental optical light, and it makes them completely opaque at visible wavelengths. So it creates a beautiful image. And the main reason is because it's not something we typically see. Now I must admit, with winter upon us here in Missouri, there are a million bugs all over the place. We have these little gnats that land on you and bite you, and as you probably are gonna see, there is an abundance of ladybugs all over the place. You should see my house. It's coated with ladybugs. They all want to get into the house before it gets too cold. But unfortunately, they keep landing on me and these little mites keep biting me. So how do we detect what a dark nebula actually is or where they're located? Well, they're most obvious when they're located in front of, say, a bright emission nebula, such as the Horsehead Nebula located in Orion, or a region that is very rich with stars, right? We get all this illumination back here, and then the dark nebula is here, and you're located here. So all the starlight either goes through it or stops as a result of that dark nebula being there. And it's basically a cloud of dust. So it can disperse light or it can stop it entirely if it's thick enough. So now something that I had to go and learn myself is the average temperature inside some of these dark nebulae can range from anywhere from 10 degrees Kelvin up to 100 degrees Kelvin, which allows hydrogen molecules to form. And that's where we get star formation to start taking place. There's different sizes, right? You have small and you have large, but the large dark nebulae can actually contain over a million. Some of the large dark nebulae can actually contain over a million solar masses of material and extend over 200 parsecs. And these are typically known as your giant molecular cloud. Now the small ones are called Bok globules, which tend to be less than 3 light years, give or take, and they can contain less than probably 2,000 solar masses in total material, but that's still a lot. In the inner regions of dark nebulae, important events are always taking place. The formation of stars. Since the density in a star is immensely greater than that of a nebula, star formation must occur through condensation. So the force of gravity in the nebula is constantly pulling it together and working against the disruptive collisions of any one nebula or cloud with its neighbors and against pressure divided by an internal magnetic field. Even if gravity can hold the cloud together against opposing forces, the cloud cannot collapse unless it can cool. So gravitational energy is released in a contraction and would heat the gas cloud, thus increasing the outward pressure and preventing a collapse any further. The dust grains are efficient emitters of infrared radiation, which escapes, right? And that's typically how something like James Webb can see these stars that are inside of these clouds with the infrared spectrum. A cloud, therefore, contracts under its own gravity, radiating away half of the gravitational energy of the contraction, the other half going into heating the gas. So as it contracts, the density and the gravitational binding increases until finally the cloud's gravity dominates the internal pressure that the material rushes inward in almost a free fall. So while the entire cloud has been collapsing, it does not have a smooth density distribution, but rather consists of a chaotic jumble of smaller clouds. And these cloudlets pull themselves together by their own gravity into proto-stars, each of which is destined to be an individual stellar system. So with that, most of these proto-stars are actually smaller than one solar mass, but a very few, maybe several, maybe up to even 100 times as massive as our sun. These few massive stars have a profound influence, though, on the evolution of the nebula. Each protostar collapses incredibly quickly. Its gases fall inward in a free fall, right? A protostar can collapse from the size equal to the outer diameter of our entire solar system to about 30 times the sun's size, which is roughly Mercury's orbit, in about 6 months. So after it reaches that size, the material becomes so hot that it has to become a star. That is, an opaque body radiating energy only from its surface. Around it is a whirling ring of cold, dusty material, which will also break up into even smaller fragments known as protoplanets. So that's basically how we got here. It is now believed that planetary systems are made out of dusty chaos. Such newly formed stars will also continue to contract, becoming hotter, but less luminous in the process until they start to produce heat by converting hydrogen into helium, rather than by contracting. If massive enough, a star ionizes the nebular material surrounding it, producing bright emission nebulae all around it. With all of that in mind, and it was a lot to take in, let's take a look at LDN 1295 and LDN 1251, as one day they might become an infant star that has yet to be born and might create planets that have yet to be formed. Keep in mind, the Earth is over 4 billion years old. That means all of this dust at one point in time came together to help make us. So at this point, let's just go ahead and look at what this looks like. We're going to use this telescope here behind me. It is, of course, the Explorer Scientific 127 carbon fiber ED triplet. Thanks for joining. Be sure to subscribe, hit that thumbs up if you enjoy the images here at the end, and clear skies, and we'll see you next time.